Last time we talked a bit about three-dimensional space, about what is a vector, what does the equality of vector mean, what does equality of two vectors mean, what are components of vectors, and so on. And we talked about how vectors add and subtract, and we talked about how scalars multiply against vectors. So if I have a real number times a vector, we talked about how that works. Something that we avoided is the idea of, well, what happens when we want to multiply a vector by another vector? So if I say multiply a vector by the number 3, that's kind of like adding the vector to itself 3 times, and we just stack the initial point and terminal point, right? We draw the vector once, we put a copy of that vector with the initial point at the terminal point of the first vector, and then we make another copy and we put that initial point of the third vector at the terminal point of the second, and that net vector from the first initial point to the last terminal point would be like 3 times that vector. So that's kind of a sensible thing to do, right? A scalar multiple. If I had, 3 times u, that's just u attached to itself 3 times. It's just 3 times as long as u. But what if I have a vector times a vector? Well, when we think of multiplication in the sense of repeated addition, if I repeatedly add vectors, that's like a scalar multiple. So I don't really have a natural way of coming up with a good idea of what I mean by a vector multiplying another vector. And that's what we're going to talk about today. And it turns out there are kind of 2 ways of multiplying vectors by other vectors that we're going to talk about that tend to be useful in applications. One of them is called the dot product, and the other is called the cross product. So these are going to be 2 different ways of multiplying one vector by another vector. Okay. So definition of the dot product. If the vector u has components u1, u2, u3, we'll deal with 3-dimensional vectors here. For the dot product, we could also be talking about 2-dimensional vectors or 10-dimensional vectors. It doesn't much matter for the dot product. Does kind of matter for the cross product though. And if v is v1, v2, v3, then we say the dot product of u and v denoted u dot v. So using, the kind of dot that we typically use for, shorthand for kind of multiplying scalars together. Here we're using that notation to indicate a vector dot product with another vector. We define that by u dot v is, so what do we do here? We multiply component-wise, and then we add together. If you're familiar with Excel, you might know the sum product function that kind of does this kind of thing. Or if you've taken stats before, you kind of maybe to find an expected value, you want to compute a weighted average, you multiply the outcomes by the probabilities, line by line, then add them together. That's kind of the feeling of this dot product. So we take the first component of u, the first component of v, we multiply them together. We do the same with the second components and the same with the third components. And then we take each of those results and add them together. This is well defined because the components of vectors are real numbers. So when we say multiply here, we're just multiplying 2 numbers together, u1, v1, that's just number times number. So these components of vectors are just real numbers. So there's no ambiguity about what we mean by multiplying u1 times v1 down here. That's just standard old multiplication. And same with addition. This is just adding numbers together. So if we wanted to be even a little more explicit, we could say that this is in, and hit the wrong button there, but we could say that this is a real number. Just to be clear about that, we take the dot product of 2 vectors, we multiply real numbers by real numbers, and then add the result together. That is a real number. The dot product is sometimes, unfortunately, sometimes called the scalar product of the 2 vectors because it does result in a real number. It results in a scalar. But note that this is not, this is not saying that it acts like a scalar times a vector. It doesn't really act that way. It's the scalar product because it's the product of the vectors that results in a scalar. Well, see, the cross product does not result in a real number at the end of it. The cross product of two vectors results in a vector. So sometimes you'll hear this called the scalar product of two vectors. Sometimes you'll hear it called the inner product of two vectors in a different context, in kind of linear algebra contexts. We often call these inner products. Particularly in the inner product case, it's often denoted this way, with angle brackets, and then u bar, vertical bar, or u vector, vertical bar, v vector. And you might actually recognize this. I know a lot of you are interested in physics and so on, and you might recognize this bra-ket notation from kind of physics and particularly quantum mechanics. You might have seen these, what they call the bras and the kets floating around, these kind of like, one side or the other side of this inner product idea here. And that notion is very closely related to this notion. Not exactly, but quite closely related. As a side note, sometimes this irks math folks, but sometimes in more applied books, maybe like physics or maybe like engineering, you might just see u bar v bar. So you might see something written like this, just u bar v bar, and that typically means the dot product. That's kind of bad form in the minds of mathematicians because that can be a little ambiguous. If you get into linear algebra, there is a proper way that you could write one vector times the transpose of the other, and that would be okay. But for our purposes, we will not take that shortcut. Would always write u bar dot v bar. Some properties. Note that the dot product of a vector with itself, what would that be? That would be u1 times u1, or u1 squared, plus u2 squared, plus u3 squared. Well, that's the square of the length, right? That's the thing that's under the square root when we compute the length of a vector. So vector dot itself is the square of its length. Or analogously, the length of a vector is the square root of the dot product of that vector with itself. We have a distributive property. The dot product distributes over vector addition. U dotted with v plus w is u dotted with v plus u dotted with w. The dot product of the u vector with the zero vector, the vector that has all of its components 0. So u1, u2, u3 dot 0, 0, 0. Well, of course, that's just 0, right? That's just u1 times the number 0 plus u2 times the number 0 plus u3 times the number 0. Of course, that is 0. That is the real number 0. So u bar, or the vector u dotted with the vector 0, gives me the scalar 0, the real number 0. The dot product's commutative because of the commutativity of each of these regular multiplications in here. u1 times v1 is the same as v1 times u1. So we can switch all of them, pull them back apart, and see that u dot v is v dot u. And scalar multiplication over dot product is associative. So if I have c times u bar, that's cu1, cu2, cu3. That just gives me cu1 v1 plus cu2 v2 plus cu3 v3. I can factor the c out, and I get c times the dot product of u and v. Or for that matter, I can make it u dot the vector cv. I could attach the c's to the v's and then view that as a dot product of u with cv. So an important theorem, if theta is the angle between the vectors u and v, so if we think of these vectors, if their initial points were put at the same location, there would be an angle between them, provided one of them is not the zero vector. There would be an angle between them. So if theta is that angle, then the dot product of u and v is length u, length v, cos theta. Or we can rearrange that and we can find a formula for the angle between the two vectors. This is quite important to know, and this is a quite important relation in things like physics when we're trying to find resultant vectors of, maybe two forces acting on an object or something like that. So there's an angle between, and it's related to the dot product this way through the cosine. And a corollary is that two vectors u and v are orthogonal. In other words, they meet at a right angle. If and only if their dot product is 0. Because that means the angle between them is 90 degrees or pi over 2, and the cosine of that is 0. So they're orthogonal if and only if their dot product is 0. Okay. Moving on to the cross product. So the definition of the cross product, again, we have two vectors, both in R3, and that is fairly important for the cross product that there are three-dimensional vectors. If u bar is u1, u2, u3, and v bar is v1, v2, v3, then we say the cross product of u and v. I have a typo there. The cross product of u and v is u cross v. And we define it as follows. U cross v is, note that this is a vector. The cross product of two vectors is a vector. And it's given by this complicated vector, where the first component is u2v3 minus u3v2. The second component is u3v1 minus u1v3. The third component is u1v2 minus u2v1. So note that the first component of the resulting vector does not contain either of the first components of u and v. And the same can be said of the second and third components. So two notes. The cross product is a vector that is orthogonal to both u and v. In other words, another way of saying that, if we say that w is u cross v, well, what did it mean to be orthogonal? That meant that the dot product is 0. So the cross product, if we call that resulting vector, let's say w, the cross product between u and v, then w dot u is 0 and w dot v is 0. And that's fairly straightforward to check. So if I have two vectors, I'm in three-dimensional space, maybe I have, in my x, y, z, all right. My x, y, z coordinate system. Maybe I have one vector like that, and I have another vector like this. Let's say this right-hand vector is kind of roughly in the YZ plane, and this left-hand vector maybe is kind of in the XZ plane, but pointing a little towards the negative direction of Y. Then the resultant vector is going to be orthogonal to those, but it could go this way or that way and still be orthogonal, right? it could be perpendicular to both vectors, but kind of in either direction. So we need to resolve which direction does it go. So let's call this one U. And let's call this one V. And the resolution is to use what's called the right-hand rule. We have to come up with a convention for which way the cross product should point, and we choose to impose this condition. We have two ways that kind of naturally speaking, if we just said the cross product is orthogonal to both of the vectors that make it up, there are two ways to resolve that. We just have to decide which way that's going to go. The right-hand rule, U cross V. So we take U cross with V. I'm getting like, my phone is like getting blown up this morning. I have a call from another professor. Hopefully everything's okay. Anyway, so if we take U cross V, we would imagine taking our right hand. So if you forget which one's your right hand, just hold them out flat in front of you. And the one that makes an L from your fingers to your thumb is your left hand. The other one is your right hand. So U cross V, take the fingers of your right hand, wrap them from U to V. So as I'm looking at the screen, I would take my right hand and wrap my fingers from right to left in this case. So that my thumb is kind of pointing at my face. In the direction my thumb points when I wrap from U to V for U cross V, the direction my thumb points is the direction of the cross product. So the direction of the cross product will be this way, U cross V. Something to note is U cross V is negative of V cross U, right? If I were to imagine my respecting my right hand rule with V cross U, I'd start my fingers curling from V to U. That's a little hard to kind of do with my hand, but going the opposite way. And now my thumb points away from me. V cross U points in the opposite direction. So geometrically, we can see that V cross U is going to be negative of U cross V. It's kind of in the same direction, so to speak, but exactly negative. And up here, we can see that, U2V3 and U3V2, if we were to switch the U's and the V's, that just results in a negative sign. And the same for component 2 and component 3. So we can see this relationship algebraically, we can see it geometrically. Note that U cross U is 0. So that's a little less obvious why that should be the case geometrically, but we can see algebraically that's pretty clear. U cross U is just U2, U3 minus U3, U2, that's 0, and the same for components 2 and 3. So algebraically, this is pretty clear. And then a third property is that if I take U cross V, so I take this cross product that is a vector, and I can imagine that, so now I'm going to draw U and V in this 2D plane that's the screen. I can imagine that if I had the parallelogram, we talked about the parallelogram rule last time, this parallelogram where I start at the terminal point of U and move parallel to V. I just start another vector V at that terminal point, and then vice versa for the terminal point of V, putting the vector U there. That creates a parallelogram. This parallelogram has a two-dimensional area. And it turns out we can find the area as the length of the vector U cross V. So the length of this vector U cross V is the area of this parallelogram. Kind of an interesting relationship. I don't think that that's obvious from the geometry. and a couple of theorems. We have a related theorem to the dot product theorem, where if theta is the angle between u and v, then u dot v is length u, length v cos theta. If theta is the angle between u and v, then u cross v is length u, length v sine theta. And the corollary, two vectors we would say are parallel if and only if u cross v is 0. So two vectors are orthogonal or perpendicular if and only if u dot v is 0. And two vectors are parallel if and only if u cross v is the 0 vector. So there's a sense in which if two vectors are orthogonal, their dot product is 0. And if they're parallel, their cross product is kind of 0. So the dot product is kind of, loosely speaking, a measure of how parallel two vectors are. When they're parallel, when it's just the same vector, we get the maximal dot product, the length squared of one of the vectors. And when they're perpendicular, our dot product is 0. So the more parallel they are, the kind of bigger in a sense the dot product is. The more perpendicular they are, the closer to 0 it is. So dot product is, roughly speaking, kind of a measure of how parallel the vectors are. And then cross product is kind of, roughly speaking, a measure of how perpendicular the vectors are. Excuse me for 1 second. Okay, and then one last note that I would like to make on determinants and cofactor expansion. So this is a bit of a foray into some ideas related to linear algebra. So we're obviously not going to do a proper treatment of what determinants mean or anything like that from a linear algebra standpoint. But we note that this definition is kind of annoying to remember. So it would be nice if we had a trick that we could use to remember that. So let's consider u cross v. How can I remember what the components of u cross v are? Well, what I can do is I can compute the determinant of something. The determinant is written in this kind of absolute value form. And I'm going to have a 3x3 grid of numbers in here, a matrix of numbers. If you remember, anything about matrices from, algebra 2 or intermediate algebra, something like that. I'm going to have a first, second, and third row, first, second, and third column. My second row is going to be the components of u. My third row is going to be the components of v. And my first row is going to be these special vectors, I hat, j hat, k hat. I can compute a 3x3 determinant in a couple ways. One way to do it, kind of the way that I like to do it, you might have seen this before, you may not have, is I can take I hat, and then I can kind of forget about the row and column that I hat is in, and I can focus on this 2x2 block, these 4 numbers here. I can take u2 v3, so multiplying along that diagonal, subtract off u3 v2, multiplying on the other diagonal. So u2 v3 minus u3 v2. Then next I want to look at j hat. I have to subtract off j hat. I alternate the sign. I knock out the row and column that j hat is in, and I'm left with these four numbers that I could imagine being like a 2x2 grid again, these four numbers, u1, u3, v1, v3, and I can multiply this way, u1, v3 minus u3, v1. And then lastly, I can go to k hat. I'll switch the sign again. Forget about the row and the column. And I see I have this group of four numbers here. And I can do u1, v2 minus u2, v1. So I can do that. This is called cofactor expansion. And if you've done a little bit of work with matrices before, if you've seen them, this might look familiar. If you haven't seen them, this might not look familiar. That's fine. Let me get rid of this and give myself a little extra space here. For 3x3 determinants, there's a nice little trick. So let's actually just copy this down. There's a nice little trick that we can do. And is this. I see that I have three columns sitting next to one another. I can make a copy of this column off to the right. I can make a copy of this column off to the right. And then I can look at these diagonals. Going from top left to bottom right, I'm going to take those with a plus. So I have I hat times u2, v3 plus j hat times u3, v1 plus k hat times u1, v2, u1, v2. And then what I'm going to do is I'm going to go the other diagonals, this one, and this one, and I'm going to bring those in with a minus. So I have a contribution to k hat of a minus u2, v1. I have a contribution to the I hat bit of a minus u3, v2. And I have a contribution to the j hat coefficient of a minus u1, v3. So this is kind of a trick that works for 3x3s. I don't think it works for any other dimension. And to be completely honest, I'm not sure why it works. I think it might be just a coincidence. Maybe there's something very deep that, that makes this work out. But I think it's kind of just a coincidence that it works this way. Although, it is possible that there's something deeper that makes this work this way, but it doesn't work for all dimensions, certainly, which makes me kind of suspect that it's a bit of a coincidence that you can do this. But if you have, a little bit of experience with working with matrices or anything from algebra, some of these ideas might look familiar. Like if you solve linear systems using Cramer's rule, that deals with finding determinants of often 2x2 determinants, and we can see that this is just I hat times a 2x2 determinant. Or you might have even seen 3x3 determinants using Cramer's rule. But depending on who you had for algebra or how far you went in algebra, you might or might not have seen some of this before.